Hi everyone, I'm William Moses and I'm going to be presenting some work that's joint between myself and Johannes on cross-translation unit optimization via annotated headers that we've lovingly decided to call header time optimization. So, writing optimizable code is hard. So I have a question for you. Suppose that I have a norm function that computes the magnitude of a vector declared in, say, an external library or a different function or something like that. And I decide to use it in this way inside of a normalized function. Now, the good thing that we want the compiler to do in this particular instance is we want it to realize that norm can be hoisted outside of the loop via loop invariant code motion, changing our O of n squared algorithm to an O of n algorithm. And what do we do to make sure that norm is actually hoisted outside of the loop, and as a consequence, also normalized gets vectorized? So the first thing that we can try to do is we can say add restrict to the pointers on top of normalize, which prevents a conflict between in and out and potentially overwriting the same data, which would mean that you'd get a different magnitude every iteration. Unfortunately, this doesn't quite work yet, so let's make sure that the compiler now knows that the input is actually constant. So since we're not actually changing the value of the pointer a inside of norm or inside of normalize, then maybe it'll now do it. Unfortunately, that still doesn't happen. Let's really make sure that the compiler knows that the call to the norm function is pure. We added that attribute pure on top of it. So now theoretically it's pure and we should be able to hoist it outside. Unfortunately, this still doesn't work because pure means that, well, it's constant with respect to the memory that comes in. It could still read global memory, and if that global alias is with output, then that might lead to some inconsistency. So what if we mark it that we can vectorize it, we can interleave it? This last time, again, it still doesn't actually work. So the point behind this is that being able to properly do this is actually quite hard. And the actual solution that we want in LLVM speak is we want the function called norm to be marked as read-only and argmem only, which specifically indicates that it only reads from the memory passed into an argument. And then that specifically happens. Note that this particular syntax actually doesn't exist in mainline Clang, and I wasn't able to find a way that did exist in mainline Clang to actually represent this. Now, this actually turns out to be a problem in real programs. For example, in this DOE RS benchmark, if you just add read none to the fast complex exponential function that's declared in an external translation unit, you get a 7% speed up to the entire program. Not just like the part of the program that uses this for loop, but the entire program. And you also get an extra 1% for no unwind, but that's a little less dramatic. So how do we make this program automatically optimizable? So the idea is that LLVM automatically derives most of these attributes as part of the compilation process and then probably decides to throw this away once it's finished compiling your particular source. So let's do something to make sure that this information is really accessible across individual translation units. So one thing that you could do is you could try to run LTO, and LTO will indeed solve this problem. But there are some instances in which LTO might not be the best tool for your problem. For instance, LTO adds an extra burden on top of compile times. It might require a lot of extra work to set up with a gold linker on top of your builder operating system, or even worse, it might actually be impossible to use LTO on your entire program because you say apt-get installed a library, and that library doesn't come with the LLVM bitcode that allows you to run LTO on top of it. Furthermore, it's also really interesting, just as a scientific question, to ask how much of LTO speedups come from these hopefully easily fixable function attributes rather than some more intense interpretable procedural analysis or inlining or something like this. As a consequence, we thus introduce header time optimization, and hopefully you see the joke as to why it's called header time optimization. So now at the end of the compilation process, let's denote what the compiler actually learned about your function using the existing analyses and Johannes's attributor pass that he added to mainline recently. And there's three modes that you can use this. The first one is remark mode, in which we'll just print out an optimization remark for any new attributes that we learned, so then the programmer can go and say, you know, this function actually was read-only, let's go mark it as read-only. The second is pipeline mode, in which we will generate you a new header for your program, and then you can just include this header, and then you'll get all of the speedups. And a third mode is a diff mode, which will provide you a diff to go apply to your original source tree. And the really surprising thing from this is that just these annotations on the headers alone account for half of the speedups that LTO was able to find. So there's really a lot of speed being left on the table by not adding these extra attributes. So how does this work? If we actually want to run it, we can take our original source code, we can add a new flag -r annotations, and it will politely say, you should probably add these particular attributes on top of your function. So if you want to surgically realize that, oh, this function takes a really long time in your program and go fix it, you can run this and realize that, oh, I really want to add this to that function. The second mode is this pipeline mode. So the first thing that we do is we take all of our source files for whatever we're trying to compile. We, inside of our make file, instead of calling Clang, we use Clang with -hto dir equals whatever directory you want to put it inside of, and it'll nicely create for us, for every individual source file, a new header file that includes a version of the header with all this information put on top of it. If we then want to go and compile this again, we can just simply include via whatever mechanism you like to include things. I like to include things by the -include flag. And then it'll take that information into account when it now goes to actually compile the executable. Another sort of variant of this that's particularly useful is, again, for libraries, in which suppose that I'm a library writer, I write my libsum.c, I go compile with HTO put on, and I create a new header as well as my library function. Now when I go have it put on Ubuntu's package repository, I include both the library as well as this annotated header, which means that these end users who want to go and include my library get to have these advantageous headers put on top of it, which is a place that LTO wouldn't really be able to work as much in practice, and then you're able to get these faster executables. So what do the header files look like in practice? So as I mentioned, HTO creates new files in a given directory that can be included by any C or C++ program. The way we do this is we leverage forward declarations. So it turns out in C or C++, for most functions, you're allowed to forward declare them ahead of time, except now we've added the extra attributes. This also requires the fact that we can also forward declare structs or classes, which we do so as such. The second thing that we added is we added new attributes to Clang to be able to represent all of the LLVM attributes. And the reason is because not all LLVM attributes that are useful for doing optimizations, as we saw earlier, are necessarily easily representable with existing C or C++ attributes. Also, our plan is to be able to transition the ones that do exist inside of C or C++ over into the existing C or C++ attributes, but as far as making a minimum viable sort of experiment, having it just output all of them in a consistent way like this was slightly easier. So, as for experiments, we ran all of the multi-source benchmarks in LLVM's big test suite, which includes a bunch of DOE proxy apps, Bitstream benchmark suite, a TSVC benchmark suite, NIST benchmark suite, and basically a bunch of different concatenated benchmark suites. We specifically selected tests with a runtime of greater than half a second, so then we could get some reasonable difference in performance, and this led to having 84 tests that we selected from there. Specifically, we ran all of these tests and took the minimum of 10 runs on a Kiest AWS C4.8x large, disabling turbo boost and hyperthreading to make sure we really get the small amount. And we compared a normal run with just 03 to using these annotated headers produced by HTO, as well as Thin LTO, and actually the quote real or fat LTO as well. So here's what we get in terms of speedups of using HTO over not using any of these annotations. So you can see for the programs on the right, we can get some pretty sizable speed boosts of like 20 to 25%. We also get some more modest speed boosts for the things in the rest, and a large swath of these where there's not much of a difference that comes in it. So let's see how this really compares against Thin LTO as an example. So specifically here on this graph, I have the HTO speedup on the y-axis. So higher means that HTO is able to get a higher speedup. We have the LTO speedup on the x-axis. Again, further to the right means a greater speedup, and that line in the diagonal means that the HTO speedup is equal to the LTO speedup, where HTO doing better is on the top left and LTO doing better is on the top right. So there's three real places of interest here. The first place is you can see in this bottom area around 0 that neither HTO nor LTO is really able to find a speedup for these programs. The second place is this bottom right sort of cluster where LTO is able to find some optimizations that HTO is not. And then this diagonal area over here where HTO is able to match LTO for those benchmarks. We also compared with, quote, fat LTO for those who are interested, and the speedups are somewhat similar, so just for ease, I'm going to talk about Thin LTO. So how does this look for the benchmarks where there's a non-zero speedup? I plotted them all right here, where in blue we get the speedups that these headers alone get us, and red is the full LTO. So specifically, if we see for the right-hand side of this graph, denoted by that line that I have right there, LTO is either better than, or HTO is better than LTO or within 2% of it for about 50% of those benchmarks. And on the left-hand side, we see that LTO is able to beat HTO for the other half of the benchmarks. And again, the really interesting thing is that more than half of those LTO speedups can be found just by those annotated headers. You don't need anything fancy. So the other interesting thing is to look at the compile and link times as well. And I've put this to be the same as in the last slide, where every benchmark corresponds, that same line corresponding to LTO being faster versus HTO being faster for those. So if you see on the left, and I cut off a lot of these sort of things, that LTO takes a significant longer period of time to run, and on the right, it's slightly more similar, but HTO still obviously gets a speed up. And what this implies is that the graphs on the left, where HTO was not able to find that speed up that LTO found, means that LTO had to do something a lot more heavy to get that optimization, since it took a lot longer of a time, implying you actually need that IPO or inlining to get the requisite speedups. So one might then go and ask, how do you actually get those speedups in practice? Like, headers that actually have the information is great and all, but does this really matter? And the answer is yes. So I've now just plot here a graph of a bunch of optimization statistics that when LLVM goes and tries to run, saying like the number of mem to reg things that are reduced, and we get 165% more than without it. You get like 30% for some CSE and related sort of pieces. Also, interestingly, we have some negatives over there, and that basically is, as opposed to the passes that go and derive the attributes that have to do so manually, we already gave them the attributes, so they don't need to rederive it. So there are some cases where there's a decrease, but it's because it has strictly more information. So interesting takeaways from this is that HTO and LTO as well can have really meaningful performance gains for programs. And the reason is that in practice, a lot of programs don't have all the attributes that they really should. And this lack of attributes therefore hinders the optimizations that we want to get those speeds, that fast performance in practice. If you use HTO, we provide you tools that will automatically integrate these attributes into your programs or libraries with just an additional compiler flag. And simply propagating these attributes alone accounts for 50%, give or take, of the speedups given by LTO, with the other 50% requiring IPO or inlining to get the extent of that full LTO. Some present limitations and future work. So at the moment, we don't generate new headers for any programs that have an anonymous struct, and we resolve that by just having a script that'll automatically generate a random name for your struct. We also similarly don't generate any new attributes for C++ member functions, since you can't forward declare that outside of the class. And similarly for an array type of a struct or class, because that's incomplete ahead of time. Once we finish the pipeline version that allows you to output a diff, so then we just add those attributes back into the code alone. Or if you wanted to manually take the remarks that we gave you and integrate them, then you also get these attributes, and as a consequence, you can get more speedups, because now you have, again, more information. And as I mentioned earlier, some future work is we want to be able to generate those standard C or C++ attributes when they actually do exist, rather than the custom LLVM ones that we have. So some overall inclusions. Properly annotating programs can make a real performance difference, but as we saw earlier, writing those programs manually can be quite difficult, especially if you have a legacy code base. We provide 3 mechanisms to be able to remedy this, one of which is support for writing LLVM annotations inside of C or C++ for the instances in which you want to, an optimization remark that will point out when you've missed these annotations that we've been able to prove actually exist in practice, and also a pipeline that will automatically inject these missing attributes into your programs. The code is available on GitHub. We plan to upstream it once it's cleaned up and submitted for publication. And I'd like to thank the DOE Computational Science Graduate Fellowship, the DOE XSL project, and Google Summer of Code for helping fund this. Thanks.
Questions? Yes.
Just a quick clarification. So with HLO, are you basically doing like an LTO run to propagate the attributes and then saying where that you should apply them? Or
So
how are you deriving?
let me step back just because the diagram might be helpful for doing this explanation. Yeah, so we do one round of compilation first to be able to identify what attributes actually exist, and then for the experiment, we then just rerun it, now including that information there. Ideally, this would be done once ahead of time or in the programming process as you actually run your code, and then you just manually actually insert these things into your program. But even with the doing it twice, we are able to get the
right. So the first one though, is it an LTO run where it's propagating these?
No, it's not an LTO run.
Okay,
It's a regular non-LTO.
So it's just saying,
compile
like for
run.
the leaf function, what kind of attributes can apply. So then, have you tried combining HTO and some kind of LTO? Because I feel, especially, well, Thin LTO has some issues propagating attributes in cross-module right now, our whole program, but at least with like full LTO, and it seems like it would be, the benefit should be multiplicative when you combine those two things.
So I have not yet, but that is a fantastic place that we hope to explore later on. But yes, they should be combinable.
So you had some places where the HTO was better than LTO. Can you explain why you had that?
Sure, let me go to the graph really fast. So like right here on the sort of left-hand side around 0. So it turns out that for a lot of LLVM optimizations that if you run them twice or with various types of heuristics, you can actually get a slowdown relative to the original program. The best example I like of this is if you try to run O3 on matrix multiply twice, you get a 33% speed up just running it twice. But if you run it on a matrix vector computation, you get a 12% slowdown because there are different like heuristics that happen to come inside of inlining and related pieces like that. Specifically because if you notice here that the slowdown, the reason that HTO tends to be faster here is because the slowdown is because LTO actually slows the code down. I'd guess that's because LTO has some of these heuristics or like running multiple optimizations twice that causes it to have a slight performance decrease. There are some places on the top over by the line where HTO is a little bit better, and I haven't investigated them too much, but my guess is there's some slight better things that can be done with like nemtereg and other pieces like this that aren't quite as dramatic, but LTO still isn't necessarily propagating the full way because of different ways that its heuristics work. That's my guess.
Once you've exposed those attributes, to like real users, if they get it wrong, obviously you'll get like incorrect compilation, right? I mean, you'll answer mismatch kind of compilation. Do you have any plan for generating warnings if you've set those attributes incorrectly?
So yes, there's two things of which the first thing is ideally by the time that this becomes user-facing that we just generate for the most part all standard C or C++ attributes rather than these, which was just easier than doing a manual translation table. But secondly, in the instances in which, say, the attributor pass or any of the existing LLVM passes that go and derive function attributes and are able to detect an inconsistency going back up, and similar to how we have an optimization remark saying you can actually add this to say you actually cannot add this because these two things can overlap.
Okay.
Hi, I'm not too familiar with this, so this might be a dumb question, but when you derive these attributes, is it through like a local analysis when you use the attributor framework? And so if you derive these with this like local analysis, when you use them in this when you use a function, does that analysis or attribute still hold? So like when you call a function, the attribute that may have existed when it was by itself, but now it's in like a new context and when it's being called, does that attribute still exist? Like, do you preserve correctness? Does that?
Sure. So the way that this works is these attributes are derived on top of the functions themselves, as opposed to at the call site. So there are additional attributes that you can derive about the call sites. And by looking at the source code of the function that you're actually calling, then independent of any place that the function is called, this should still hold because that's the actual code that's running inside of there. You do bring up an interesting point that we've considered doing just because it's also separately interesting, is you could also imagine running the equivalent of this process multiple times to be able to discover, the first run we found that this function was read-only, but the second run, because it called this read-only function, we found that this external function was also read-only. So you can also imagine sort of iterating this process as well.
Cool. Thank you.
Let's thank our speaker.